Hi, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 11th module in a series that we're recording to support the course EE221A, Linear System Theory at Berkeley. This 11th module, the topic of it is Hermitian matrices. We're going to explore a couple of properties of matrices that come out of our recent work in the previous modules in defining inner products and defining adjoint maps. So based on what we know about the definition of the adjoint, we can start looking at special cases. For example, we could look at maps A which are self-adjoint. So how do we define a self-adjoint map? So again, we're going to be working, as we have been doing, on inner products, well, generally Hilbert spaces, so complete inner product spaces. We've endowed that with an inner product, so an inner product over whatever vector space H we're looking at. And we'll be operating using a linear map A. So A is a map which is linear and continuous. A is linear and continuous. And in this case, A is going to be mapping H back to itself. So it's mapping from H to H. And so it's adjoint. A star is mapping from H to H. So we say that that map is self-adjoint if the map A is equal to its adjoint map. So A is self-adjoint if A is equal to A star. Or equivalently, using our definition of the adjoint map, this means that X, AY, is equal to AX, Y. And that has to be true for all X and Y in our Hilbert space. So a nice example of this, in the case of A being, if we just define that linear map as being matrix multiplication, or again, if we're thinking about finite dimensional vector spaces so we can represent that map A in terms of matrix multiplication, we can think about how that specializes. So what is a map that is self-adjoint? And that specializes to something called Hermitian matrices. Hermitian matrices. So now A is represented by a matrix. So I'm going to write it as A is equal to some matrix A. That's a bit of an abusive notation. That's the operator. That's the matrix. And so let's put that, where A is represented in terms of its ijth element. So its elements are called Aij, and I and J are going to range from 1 up to n. Okay, so A itself is a matrix. It's an n by n matrix in either R or C. Then the map A, so the map which is represented by matrix multiplication, is self-adjoint if and only if the matrix A is Hermitian. A equals A star, and that's, we call that being A is Hermitian. Okay, so let's think about what that means. So here, when we talk about adjoint map, we've defined star to be something quite particular. It's defined as the A star is the adjoint map of A. In matrix notation, when we talk about A star, we have another particular thing we think about, which is really Hermitian. What that really means is that A, I, J, the ijth element of A, is equal to A, J, I over bar. So what that means is the matrix A is equal to its complex conjugate transpose. So there's two operations involved in here, complex conjugate and transpose when you go from A to A star. So Hermitian matrices have the property that the matrix is equal to its complex conjugate transpose. What we've derived up here is a definition for self-adjoint maps. So this continuous linear map is self-adjoint if A is equal to A star. So that map is self-adjoint if and only if its matrix representation is Hermitian. And that's a powerful link that allows us to go back between the operator, back and forth between the operator notation and self-adjoincy of that operator notation, and something that means something quite concrete with respect to its matrix representation, which is that the matrix is equal to its complex conjugate transpose. Okay, so with that then, we can do a couple of interesting things. We can go forward and think about, for example, what's a unitary matrix? This is unitary matrix. Okay, so a unitary matrix, we'll call it U. A matrix is unitary if and only if, so we'll write it as this, a matrix U is unitary if and only if U star U is equal to UU star is equal to the identity matrix. Okay, so that means that if you think about the matrix U, an n by n matrix, if the n rows or columns of U form an orthonormal basis for Rn. And if we're dealing, for example, in simply a matrix whose elements are reals, such a matrix is called an orthogonal matrix. Okay, so now with these concepts, so the concept of self-adjoincy, the understanding of the relationship between self-adjoincy of maps and their corresponding, how their corresponding matrix representation, how the matrix representation of the map and the matrix representation of its adjoint are related to each other, and this definition of unitary matrices, we can now start to do some useful computation or useful sort of structural analysis of matrices. And one of those useful things is called a singular value decomposition. Singular value decomposition. Singular values. Let's start with the concept of singular values. Let's start with a matrix. In general, let's make it complex. Of course, this holds for reals too. In general, it's not going to be square. It doesn't have to be square. So A is an m by n matrix. If we think about A star then, okay, so A star, Hermitian transpose, and I'm multiplying it by A, that's going to be an m by n matrix. So that is a square matrix just by the definition of A star. If we look at the eigenvalues of AA star, so let lambda I be the eigenvalues, so there's going to be m of them, be the eigenvalues of AA star. We can note a few things. First of all, AA star is Hermitian. The eigenvalues of Hermitian matrices are always real. So that's a fact. Actually, it's something that you can prove very easily. So a Hermitian matrix always has real eigenvalues. In this case, we're looking at AA star. The eigenvalues of AA star are all real and non-negative. That's also something to prove. Let's line them up from the largest to the smallest. So let's assume that lambda 1, so they're all positive, or non-negative, I should say. Lambda 1 is greater than or equal to lambda 2, which is greater than or equal to lambda r, say, where r is less than or equal to m, which is greater than or equal to lambda m. So I've lined up those eigenvalues. And if R is the rank of the matrix A, then that's also going to be the rank of AA star. then that means that these first R eigenvalues are all positive and the remaining eigenvalues are all 0. Okay, so there's R non-zero eigenvalues of AA star. So we define the singular values of the matrix A to be the square roots of these corresponding eigenvalues. So the non-zero singular values of the matrix A are the square roots of these eigenvalues for I equals 1 up to R. And then the remaining singular values of the matrix A are 0. Okay? So for example, if you were given a 2 by 3 matrix, here's an example. A is a 2 by 3 matrix, and we'll just choose something simple, 2, 1, 0, 0, 0, 0. And you wanted to compute the singular values of the matrix A. So you can see easily just by looking at the matrix A that it has rank 1. And let's compute its singular values. So the eigenvalues, lambda I, of the matrix AA star are going to be the eigenvalues of the product. So it's going to be the square matrix 2, 1, 0, 0, 0, 0 multiplied by 2, 1, 0, 0, 0, 0. Okay, so that's A star. In this case, the elements are all real, so I just took the transpose. And if we multiply that out, we just see that's the eigenvalues of the matrix 5, 0, 0, 0. So the singular values of the matrix A are the square root of 5 and 0. Okay, so given a matrix A non-square, we have a way of computing its singular values. So how could we use this? Well, we've seen this, we've seen something like this before when we were talking about induced norms. In particular, the induced 2 norm if we remember, the induced 2 norm of a matrix, so 2 comma I, is equal to, we stated what it was. We didn't actually prove this when we went through induced norms, although I suggested it was a nice exercise to try. It's the maximum eigenvalue of the matrix product A star A to the 1/2. So you take that eigenvalue and then you take its square root. You take the largest eigenvalue and then you take its square root. That is the largest singular value of the matrix A. Okay, so here the eigenvalues of the non-zero eigenvalues of AA star are the same as the non-zero eigenvalues of A star A. Okay, so this induced 2 norm is more appropriately called the largest singular value of the matrix A. And again, it still remains to show that you can derive this relationship just from the abstract definition of the induced norm that we presented, I think, a couple of modules ago, Module 8 or Module 9. Okay, so that's where we've seen something about singular values before. But where this idea of singular values becomes quite useful when we're thinking about matrices and properties of matrices is in the singular value decomposition. And that will be the topic of the next module. So in this module, we've used our knowledge of adjoint maps, inner products, to think about Hermitian matrices, so what it means to be self-adjoint when you're thinking about the matrix representation of a linear map. We've talked about unitary matrices, and we've also talked about singular values. We've defined what singular values are, and we've related them to, at least in the 2 norm case, the induced 2 norm of a matrix. Thank you.